Welcome everyone. In today's class, we will discuss linear temporal logic. If you recollect what we have discussed in the last three classes is what is formal verification, how formal verification works, and how to write the properties also. So, we have taken one example of arbiter and where we basically identify four properties, right, but it is in those properties are in LTL, but we never discuss what is the exact syntax and semantics of that temporal logic, right. So, we need to understand exactly what is the correct way of encoding properties in LTL, otherwise you will write property which will be wrong, right. So, in today's class we will learn exactly the more detail about this the syntax and semantics of linear temporal logic. So, as I mentioned earlier also, this linear temporal logic defined over path, right. So, you basically think about the paths like this, and these paths are actually infinite, right. And I will say something holds here. So, this is my S0, this is S1, S2, S3, S4 and so on. So, I will say this path say pi, this pi holds pi satisfies some property phi if the corresponding to this property whatever requirement. See, for example, if you remember I discussed about this future, right. So, that means in some future state, let us say I am checking whether f of q holds in S0 or not, right. So, what will happen? Let us say in some state here q holds. So, then I can say that this pi satisfy f of q, because from this state in some future q holds, right. So, these things you need to understand. Always I will think about the logic or the formula on a path. And this I also discussed that this temporal logic is effectively consist of all the proposition logic plus the temporal operator. In LTL we specifically have four operator which I have already introduced in previous classes. This is x is next, f is future, g is global, and this is until is this is until, right. Since whenever you discuss this paths and all, it actually captures the time, right. So, your property will also should capture this timing behavior, right. So, something is happening here and in future something will happen, or in next state something will happen, something is holding until something else will hold and so on, right. So, that is why this four temporal operator is needed, and we can see that this four will be good enough to represent all kind of properties. Okay. So, as I mentioned we need to understand whenever any logic we are going to understand what is the syntax of that logic and what is the semantics of the logic. So, syntax means the whether what is the grammar behind the logic, that means you are writing correctly. See, right? For example, you write a C program and if you forget some semicolon after one statement, it will say there is syntax error, because it expects there should be a semicolon after each statement, right. So, similarly, you have to see what is the grammar behind the what is the correct syntax for LTL properties, right. And semantics is the meaning of the property. So, if I write a property, what does it mean, right. So, you have to understand exactly to meaning of these operators and all, so that I can understand the meaning of a complex property. And LTL is very important because most of the hardware verification, this is a natural choice, because you think about in hardware we always think about a trace, right. I am giving an input and hardware is going through one execution path, and I have to check whether the property holds in that path or not, right. So, this execution is kind of linear, right. So, that is why this LTL is kind of default choice for hardware verification or circuit verification. So, before going into the syntax and semantics, let us define the transition system or Kripke structure. Again, if you recollect the arbiter example that I have taken in the previous class, we have the Verilog code, but we extract a finite state machine, right, or a model on which the verification will work, algorithm will work, right. So, that particular system, although I am loosely I was taking it is a finite state machine, but it is a finite state machine, but it is more called as transition system or Kripke structure here. In normal finite state machine, we always have a end state, but as I mentioned earlier also, there is no end state here. So, every state has some next state. So, that is the kind of difference between normal FSM versus the specialized FSM, which is Kripke structure or transition system. So, let us define it. It has set of states S, then you have set of transitions set of level for the state and the only start state. You do not have any end state, right. So, this is how I defined this. So, S is set of states, this is set of transitions. Transition is basically, you can think about there are many states like this in your machine, and transition is basically say this is S0, S1, S2, S3, S4, S5, right. Transition is basically from one state to another, right. So, you can think about these are the transition I have, something like this. And then the level is important. Level is basically for every state. So, L is basically map the states to some propositions. So, I define certain proposition. I will give a concrete example in today's lecture. Let us say some proper proposition P holds here, Q holds here, R holds here, P holds here, P holds here, Q holds here. So, then I will say the level of S0 is basically P. Level of, let us say in this state P, Q both holds. Level of S3 is basically P and Q, right. So, we basically see what are the atomic proposition holds in particular state. So, this is the level of the state, and S is the start state. I usually put say arrow just to mark this is the start state. So, if you see here, this is mostly same, the level is important here. For each state there are some level, because the property will be in terms of those levels, right. And then there is no end state. Okay. So, now let us come to the syntax of LTL. This is I will say the formula phi, which is in LTL, which is incorrect if it is only true or false, right. So, any true or false is LTL, correct LTL formula, or any propositions, atomic propositions or the proposition constant, right. So, individually they are also correct LTL formula. And if there is already a formula which is a LTL formula, if I take the negation of the formula, then also it is a correct formula. If I take two LTL formula phi 1 and phi 2, both are correct in syntax of LTL, and then their conjunction is also a correct LTL. Similarly, their disjunction is also a correct LTL formula, and their implication, right. And then we have 4 temporal operator. If phi some LTL property, it may not be a proposition, it can be a property, right, which is LTL property, then x of phi is also correct LTL, f of phi and g of phi, right. All three are correct LTL formula. And if there are phi 1 and phi 2 both are correct LTL formula, then phi 1 until phi 2 is also a correct LTL formula. Let us try to give you an example. Let us say P and Q. This is a LTL formula, because individually they are, P is atomic proposition, Q is atomic proposition, and then I am saying they are and then I can say this is F, right. So, F of this. So, this is a correct LTL formula, and I can say this globally true. This is also correct formula. So, this is one formula, say phi 1, and I say this is until R, right. So, this is my phi 2. So, this is also valid LTL formula, and say this holds if say A implies, right, this. So, this is also LTL formula, because this is LTL formula phi 1, this is LTL formula sorry phi 1 and this is phi 2. So, phi 1 implies phi 2 is also LTL formula, and then this holds globally. So, this is also LTL formula. So, you can understand here, if I just build up from the scratch from atomic proposition and combining very small LTL formula, I can get a very complex LTL formula, and that is actually correct. But if you try to write a formula like this, which is incorrect, right. So, if you try to write F G X, so there is no proposition, right. But if I write F G X P, this is correct, because P is a correct LTL formula. So, X of P is a correct formula, then globally X P is correct formula, and in future globally this will hold, this is also correct formula. So, this is correct, but if you write say F G P Q, this is not, right, or F or G Q, this is correct, not this is not correct, because this temporal operator should always come with some LTL formula, but here it is not, right. So, I hope you understand, and there are quite few examples are given here. So, these are all correct, and you can understand this F of P is correct, G of Q is correct. So, this is a correct LTL formula, implies P until Q, this is correct, F G P is correct, P implies GQ until not Q until P, this is also correct. So, you have to build up right from small proposition to the bigger formula. Similarly, this is also correct, GFP implies F of Q until R, right. So, these are all correct formula, P until Q until R also. Okay. So, I hope you understand the syntax. So, given a LTL formula, whether this is in correct syntax or not, I hope you will be able to identify, okay. Or given a property, you will be able to encode now with correct syntax with this knowledge. There is one more thing you need to understand. See, for example, here I am writing different operator, right. If I parenthesize it, it is fine, right. So, for example, I am writing here FP and GQ implies P until Q. So, now what is the meaning of this? Because you may think about that this holds tightly, this hold tightly, right. So, if I take this example here, say FP and GQ implies P until Q, right. So, you have this formula. Now, you do not give any parenthesis. So, now you need to understand the precedence of the operator, so that I know what is the exact meaning of that, right. This is until. So, precedence is all the unary connecting has the highest precedence, not X, F and G, then until the temporal binary operator and then logical operator and or this. So, now if you see here, the highest priority will be this, this, this and then this, right. Because again you might get confused whether there is still confusion, right. So, for example, whether this is fine, this is fine, this is also fine. Now, for this implication, should I take GQ or F and GQ, right, FP and GQ. So, that is as per here it can be anything, because they have the same interpretation, right. So, that is why if you want this, you should put a bracket here. So, ideally when you write a formula, if you are not sure about the precedence, you should always put parenthesis to make this, you understand. So, for example, you have P until Q until R. Should I consider P until Q until R or P until Q until R? So, they are not same. I will give an example at the end of the class to show that they are not actually same, okay, once I include the semantics. So, you should not write a property like this which is ambiguous. If you want this, you put a bracket here. If you want this, you put a bracket here, right. Similarly, here also, if you want this, you should put a bracket here, right. So, if you want this, you should put a bracket here and you put a bracket here and so on. Whatever you want, you put parenthesis. So, then there is no confusion or ambiguity in your formula, okay. So, as I discuss that this semantics, I have to discuss the meaning of that. So, you have to now define the path or the trace on which this formula will be defined, right. For example, I could not explain what is P until Q until R, what is the difference between these two, because I have not introduced the semantics yet. So, let us define the path, because semantics will be defined on the path. So, we iteratively use trace or path, both are okay, right. It is basically a sequence of state transitions. Say, for example, if I take my example of this FSM, I can say that this is one path starting from here, it is going here and it is rotating here, and sorry, it should go like this, right, and it is going here, say, because it should be infinite, right, and so on, or here, or maybe it can go here and then it starts rotating here, because it has to be infinite, okay. So, you have to have transition, you cannot just have a S1 to S2 unless there is a transition between them, right. So, it is basically a sequence of states, but they follow the transition of the system, but this is infinite. So, I put a dot dot, there is no end of it. And then we just, if this is pi, I say pi I is the ith state, the path starting from ith state. So, for example, if I do pi 2, it means nothing but starting path from S2. So, S2, S3, S4 and so on. Original path was S1, S2, S3 and S4. So, if I write a pi 3, the path starting from S3, S4, S5, S6 and so on. Okay. This is the definition. Now, I will define the semantics of LTL. So, so it is basically defined over a transition system, which I have already defined, and this property holds on a transition system M if phi holds on all paths starting from the start state of this. So, effectively I will write M S satisfy path or simply M satisfy phi. So, what I am saying, it is very important to note this all paths, right. So, I am saying this M satisfying the formula phi, it means I have the start state, there will be many paths from this, right. In all path phi should hold, then only I will say this M satisfy, this is the start state. So, either I will write M S satisfy phi or simply M satisfy phi. So, this is very important to note, right. Now, let us define all possible scenarios and their semantics. Okay. So, I have already considered a path pi, which is S1, S2, S3 infinite in this transition system M. I am saying the formula some formula phi holds in this path, and I am just defining how it is happening in one path, and then you can use the same notion for all paths, right. So, I will say the formula, if the formula is a true, so it is the pi satisfy true, if pi does not satisfy false, this is obvious, right. And then I am saying pi satisfy the some proposition p. What does it mean? You basically have, let me just draw the pi here. So, you have some S1, S2, S3, S4, S5 and so on. I am saying this pi holds proposition p if the label of the start state is p. So, if p holds here, then I will say the pi satisfy p, because the start state of that it holds, right. Then if I say pi satisfy negation of p, if pi does not satisfy phi, it is obvious, right. If I identify that some formula phi which pi does not satisfy implies pi satisfy negation of the formula, which is very obvious, right. Then if the formula pi satisfy phi 1 and phi 2, if pi satisfy phi 1 and pi satisfy phi 2 individually, right. So, you think about that a simple example, let us say again I am taking the same example S1, S2, S3, S4, S5 and so on. I am saying let us say in this state p holds, in this state q holds. So, in this let us say phi 1 is f of p. So, in this state S1 this pi satisfy future p, right. So, that means pi satisfy f of p, because in starting from this some state p holds. Then I am saying the pi satisfy the say phi 2 is future of q. Then pi also satisfy future of q, because in some future state is happening. Then I will say satisfy pi satisfy f of p and f of q, because it satisfies both the formulas, understood. And similarly, if pi satisfy phi 1 or phi 2, if it satisfies this or this, right, which is understandable, because if one of them satisfy, then it will satisfy their or disjunction, right. Similarly, for implication, so it is basically not phi 1 or phi 2, right. Implication means phi 1 implies phi 2, it is basically this. So, it basically this, and so to make this formula true, if phi 1 holds, so whenever phi 2 holds, phi 1 has to hold, right. So, if you draw this truth table 0 0 0 1 1 0 and 1 1, this is very obvious. If you know that the output this is say p and this is q, or say phi 1 and phi 2, then phi 1 implies phi 2. So, this is if it is 1 and this is true, this is true, this is true, but this is false, right, or this is 0. So, effectively if this is 0, I do not care about phi 2, but if it is 1, then phi 2 has to 1, right. This is what I have written here. If pi satisfy phi 2, then phi 1 has to also hold, otherwise I do not care. Okay. And the next is next phi means in the next state phi holds, right. So, that means pi 2 satisfy phi, right. So, it is interesting. So, I will basically give an example. let us say I have taken one example. I have this state S1, S2, S3, S4, S5 and say there is a loop here. Okay. And let us say I have here Q holes, Q holes, Q holes, Q holes, right. So, now if you think about a path starting from S2, right. So, here Q holes, Q holes, Q holes, Q holes and all. So, I will say this globally Q holes, right. So, I will say this state satisfy this state S2, right. So, this state S2 satisfy globally Q. So, then this is effectively means phi 2 satisfy globally Q, because pi is starting from S1, but S1 does not satisfy globally Q, because in this state Q does not hold, right. Globally means in all states should hold in that path, and it is infinite. So, it will be S4, S5, S4, S5. So, it will be always true Q, right. So, this is what is happening here. So, I will say pi holds in the next state if the next state holds phi, right. This is the example I have given. So, in this state globally Q holds and say this is my phi, right. So, phi is globally Q. So, I am saying that phi holds here in this state pi 2 for the path starting from S2 phi holds, then pi satisfy next of phi, okay. In the next state that phi should hold. Similarly, this f phi in some future state phi should hold, some pi I, right. It has to hold, it is, you cannot say it never holds, some future state where pi I holds. If I take the same example again, I will say that here future of p, right, because in p holds in future. So, I will say this state, this is pi satisfy future p, right, because p is holding in some future, and this may be a big formula also. So, I try to give an example here with a formula phi, here I give an example where phi is just a progression. So, understood, but here important to know that this future is starting with the start state also, right. So, it is I greater than equal to 1, and if you recollect my start from S1. So, if I have a scenario where p holds here itself and it does not hold here, say, right, then also future holds, right. So, future includes the current state, if p holds here also, this pi satisfy f p, because S1 satisfy p. So, future includes start state, right, future includes the start state as well. So, people might get confused that future means not the start state, but some future state, but future include also the current state, okay. Start state or the current state, okay. So, globally phi again it has to hold every state, all state of that path, right. If I think about a path S1, S2, S3, S4 and let us say this, and if I say this this path pi satisfy globally p, then p has to hold here, p has to hold here, p has to hold here, p has to hold here. And you remember this path is basically infinite path, because there is a loop at the last state. So, it has to hold in all states pi I. So, all pi I should hold phi. The last one is phi 1 until phi 2. So, here in this phi 1 until phi 2, I am saying this some path satisfy phi 1 and phi 2, there exists some state I such that pi I satisfy phi 2, and all state for all j till I minus 1 phi j satisfy phi 1, right. Let me take an example, S1, S2, S3, S4, S5 and so on, right. So, I have this. So, I am saying that say in some state q holds, right. So, this is my I equal to 4. So, I am saying that there exists some I which is greater than or equal to 1. So, let us say this is 4, in that state Q holds, right. So, that means here S4 satisfy Q, S4 is satisfying Q. Then all states starting from the first state till this state. So, that means S1, S2 and S3, in this state P must hold, because I am checking P until Q. So, I am saying S4 satisfying Q, then all the previous state P holds here. Okay. So, that means all the state till the state where Q holds, P must hold. Okay. So, then I will say in this state, if this is pi, then pi satisfy P until Q. Now, you might question whether P should hold here or not, it does not matter. As long as in all the states starting till this state P holds, P until Q holds, I do not care about whether P holds in S4, S5 or not. That is not my checking. I have to check in S1, S2 and S3 P must hold, because this is the first state where I got Q holds. Okay. But very important to note here again, this there exists I which is greater than or equal to 1. So, it means it might be the scenario where if you think about the path S1, S2, S3, S4 and so on, it may happen that Q holds here and P never holds, right. So, then Q holds in S1, then also I will say this is say pi 1. So, then also pi 1 satisfy P until Q. This is very important to note, because I have the objective to check the state where Q holds, all previous state P must hold, right. But if Q holds even in the first state, then also I will say P until Q holds. Okay. So, this is very important to note. Quick thing. So, if your FSM is given like this, there is a end state, right, which is the normal FSM. What I can do? I can simply add a dummy state and then I put a infinite loop here. So, then this will become an infinite system. So, that there is no end state, right. This is the simple thing. So, this is what I have done. And if there are some unreachable state, what is unreachable state? If you start from this state and that state cannot be reachable, right. So, for example, this state. So, even whatever path I will try to construct here, this S4 will never come. So, I will remove this, I do not need this, right. So, I will just remove this non-reachable state and this will be my final infinite system. Okay. These are the simple ideas I am just explaining. Okay. So, let us now see the levels of a system. If you have say state bit n0, n1 and n2, here n1 true, right, here n2 true, in which this is n0 true here and here n0, n1 and n2 true, right, and here none of them is true. And I also can define some other atomic proportion which is say n0 or n1. So, n1 holds here, so P will holds here. So, Q is n2. So, n2 holds here, Q will holds here, right. Here n0 holds, so P holds here, and here n0, n1, n2 both holds. So, P also true, Q also true. So, P and Q both holds, right, and R says this, and so then R will be true here, which is not of n0, not of n0, all of them are 0. So, the level is for this state P and n1, for this state n2 and q, for this state only r, in this state q and n0, in this states p, q, n0, n1 and n2, right. This is how I will define the levels of the system of the states, right. Now, let us take example and discuss how to check whether this particular property holds in a system or not, right. So, let us check to whether M satisfy P until Q or not. So, then as I mentioned, from this state I have to identify all paths, and in every path I have to check whether P until Q holds or not. So, I will just show some paths, but there are many paths here, right. So, I will just let us take the first path. So, which is basically let us say this and then it is looping here. So, it is infinite path which is S0, S1, S4 and S4 repeats. So, here you see P holds, then Q holds here. So, I do not need to check rest. So, P until Q holds here, right. So, pi 1 satisfy P until Q. So, there is another path I have taken S0, S1, S3, right. So, S0, S1, S3 and then S1, S3, right. So, it loops here. So, S0, S1 and then it loops here. So, in this case also P holds here and Q holds here. So, in this path also this also satisfy, pi 2 also satisfy P until Q, right. Q holds until P holds. I do not need to check rest. Whenever it happens for the first time, rest of the things I do not need to check. Let me take the next path, say pi 3, which is S0, S1, S3, S0, S1, S3, then S0. So, it is basically this path. So, this path will also satisfy because P and then Q holds here. So, this pi 3 also satisfy P until Q. Let me take the next path pi 4, which is S0, S2, S3. So, maybe I will take a different color. So, it is S0, S2, S3, S0, S2, S3, then it goes back here and it loops here in this path. So, in this path P holds here, P holds here, so and then Q holds here. So, P holds here do not matter, right. So, P holds here, P holds here, P holds here, Q holds here. So, P until Q holds. So, then I will also say pi 4 satisfy P until Q. So, there are many other paths, right. So, it may happen that it loops sometime here, then it goes here, it loops sometime here, then it loops here, it loops sometime here and then it do loop this here, right. So, there are many paths. So, in a verification time, if I have to say this model satisfy, you have to check all paths. So, I have shown some paths here and all those paths this holds, and if you identify many remaining all paths, then also we can show that this P until Q holds on those paths. So, then I will say this model satisfy P until Q. Okay. Let me take one more example. So, same example, but I will just check whether M satisfy future Q. So, here it is pretty easy to show that say any path going through this transition Q holds here. So, there may be many paths which is basically of S0, then S1 and something. It may be S4, 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 or it may be S3, S1, it may be S1 and then come back to S0 and so on. So, there are many paths just starting from these transitions. Since S1 holds Q, then future of Q holds in all such path starting from S0 going through S1, right. Similarly, if you think about the other way out is this, there are two transitions. So, P holds here, P holds here, and the only way you can go here. So, here Q holds. Now, if you think about, there are only two ways you can create paths, either you go through this and do the infinite thing, or you come through this and do something, right. You come through this and then you do here and loops and whatever it is. But in this also S0, then S2, then S3 and anything. So, here Q holds, then also I can say this path also, all path of this format also satisfy f of Q, right. So, then I can say that any path starting from this start state will satisfy f of Q, then I will say yes, this model satisfy f of Q. Then quickly check whether this satisfy globally Q. And you can now clearly see that it is not. Why? If you see here for this path in the start state itself Q does not hold, right. Okay, I am checking GFQ. Okay. So, it is not globally Q. Okay, let me discuss here. So, what does it mean GFQ? It means globally future Q holds. That means, if you think about a path like this, right, you take globally means in every state, right. It is basically means in every state in the path, that is globally f of Q holds, right. Effectively you have to show that f of Q holds in every state, right. So, now let me see one path here, if we can. So, basically as I mentioned that I try to identify a path in which this globally GFQ does not hold, right. So, let me take one path and show you. Let us say I am taking this S0, then S2, then S3, then S0, and this loop will continue, basically this path, okay, and this will continue. Now, you see here P holds here, P holds here, PQ holds here and P holds here, right. Basically, you have to check future Q holds or not, right, in this state. So, I have to see for this state S0 future q holds because q holds here. So, f of q holds here, in this state q holds here, f of q holds here, right. Now, if you think about this path here, future include q. So, f of q holds here and these states only repeat, right. This is again S2, S3 and so on, right. So, then I will say in this path, if this is my path pi which satisfy GFP, because all state f of q holds, right, globally future q holds. So, this is the right path, right, this is not the counter example. Now, let me take the another path. Okay. Let us say I take this path now, the path which is starting from this here and it loops here, right. So, it is basically S0, S1, S4, S4, S4 and so on. Now, for this state P holds here, Q holds here and R holds here, R holds here, R holds here or not, right. Now, for this state in future Q holds, so f of Q holds here, right. So, this is my S0, this is S1, this is S4. In S1 future includes the current state, so f of Q holds here also, right, f of Q holds here, f of Q holds here. What about S4? Q does not hold here and it will always loop in S4, right. So, in future I will never have a state where Q holds. So, this state does not satisfy FQ. So, there is not of FQ holds here. So, for this path pi does not satisfy globally future Q, because I am found S4 where FQ does not hold. Okay. So, this is the counter example. So, in this diagram GFQ does not hold. Okay. Let me take one more example. This is probably the last example. So, just want to check whether P until Q until holds here or not. So, this is very interesting. If you see the pi 2, let me just give example. So, pi 1 was S0, S1, S4, right. So, this pi 1 was the path is this, right. This is my pi 1. So, pi 1 is S0, S1, then S4, S4, S4 and so on, right. And the pi 2 which is S0, S1, S3, S1, S3, right. So, which is S0, S1, S3 and then basically it is looping here, right, which is S0, S1, S3, S1, S3 and so on, right. Now, let us see what is happening here. So, what I have to do? I have to check P holds until Q until R holds. So, what I have to do? I have to level the state where Q until R holds, right. So, for example, if you see here P holds here, Q holds here, R holds here. So, I can say that in this state Q until R holds, right, because Q holds here and R holds in the next state. So, in this state Q until R holds, in this state also Q until R holds, because R holds means Q until R holds. In this state P holds until Q until R holds, because P holds here and in this state Q until R holds. So, then this path pi 1 satisfy P until Q until R. Now, think about other path. So, here P holds, Q holds and PQ holds and Q holds, again PQ holds and so on. So, if you see here I do not have any state where R holds, right. So, this state does not satisfy Q until R. So, this state S3 does not satisfy Q until R. This state also it does not satisfy Q until R, right. Q until R not satisfied, Q until R not satisfied, Q until R not satisfied. So, obviously, P until P holds here, but in future state Q until does not hold. So, I will say this pi 2 does not satisfy P until Q until R. Okay. I hope you understand the interpretations now. I will take one more example where is the FGP and GFP same. What this FGP? I am saying in future globally p holds, right. So, that means I will able to go to some state, right. In after that globally p holds in all state. So, you take the example here, I reach a state F4 and after that p holds all the time. So, I will say globally p holds here, globally p holds here, because in all state starting from this will hold here. So, if this is my pi, I will say pi satisfy f g p, because I from this state I go to some future state where g f p holds. And what about g f p, which is basically globally future, right. So, which is basically in every state there will be some future state in which p holds, which is basically infinitely often effectively. So, I have to see whether f p holds in all state or not, right. So, in this state f p holds, because f includes the current state, f p holds here, f p holds here, because after that in future p holds, here also f p holds, in this state also f p holds. So, I can say that globally f p holds. So, I will say this path pi satisfy globally future p. Now, let me check in this path whether f future globally p holds or not. So, I cannot found a state from where in all path all state p holds. For example, here p holds, p holds, but p does not hold here. So, if you take this loop, so in this path I cannot say that in this state globally p holds, in this state globally p holds, in this state globally p holds, because I always come back to the S3 where p does not hold. So, in this path pi f g p does not hold. Understood? So, this is very important to understand the difference between in future globally hold. So, eventually something will definitely happen, this is f g p, and g f p is infinitely often. So, this is happening infinitely often. Okay. So, I will conclude with this confusion that I ask you, that whether these two are equivalent or not. They are not equivalent, that we have already told. Let me take an example, right, S1, S2 and S3, and say S4 and is a path, this is my pi, and say p holds here, q holds here, r holds here. So, I have to check whether p until q until r holds or not. So, in this state q until r holds, because q holds and in the next state until holds. So, in this state p holds and in the next state q until r holds. So, I will say p until q until r holds, right. But for this all the state in which p until q should hold until r holds. So, in this state r holds. So, I have to make sure that S1 and S2 in both state p until q holds. So, does p until q holds here? Yes, right, p until q, because q holds here. Now, in this state p until q holds, yes, q holds here, right. So, p until q holds and then r holds here. So, in this example both are same, right. So, I can say that both p until q, so this and this holds, right. Now, if I take another example, in this example we found that both property holds, right. Now, take an example where say S1, S2, S3 and S4 and p holds here, q and p holds here and r does not hold any state. Now, let us check. So, I will check whether p until q until r holds not. So, q holds here means q until r holds and p holds here. So, I will say this pi satisfy p until q until r, because q until r holds here. Now, think about p until q. So, p holds here, q holds here. So, p until q holds here, right. So, p until q holds here, p until q holds here also, right, p until q, because q holds here, but in this state p until q does not hold, because there is no q, right, and there is no r in future. So, I do not have any state where r is future until that point p until q holds here. So, I will say this path pi does not satisfy p until q until r, because there is no r. I have two state where p until q holds, but there is no future state where r getting hold, right. So, I hope this clear that they are not equivalent. So, with this I conclude today's class.